Yeah. All right, yeah, see what you can do. Let's see, got a bunch of stuff going on in chat here. Okay, password reset worked. Good, good. Is PA1 supposed to use recursion? Not really. It's not clear. I mean, you can do anything with recursion, but I would probably do it just iteratively um, for PA1. Didn't use any structures, right? For loops or while loops should work. Did not intend recursion. Um, yes, someone points out you can use recursion for adding. This is true. You can force almost anything into recursion, but not necessarily. Um, it's not necessarily going to make your life easier, and that's sort of the main reason we use recursion is to simplify the implementation of algorithms. Or maybe, if we're going to split it up into multiple processing engines, a recursive algorithm might lend itself to that better than an iterative one, and so on. But yeah, PA1, don't worry about it. Just do a straight for loop to test primality. Put that inside a for loop to look for gold box. Put that inside a for loop to test gold box on consecutive even numbers. But don't make it just three nested for loops, right? Put each of those in a separate function, and it will simplify the implementation. Um, my Linux server login doesn't work. Should I come to office hour to fix tomorrow? Um, so let's see. I'm guessing you're not in CSE222. Um, Shoot me an email to remind me that your login doesn't work, and I will reset your login to its initial setup. Student ID followed by underscore. But double check the how-to guide on Canvas and make sure you're using the correct server name, the correct username, and the correct initial password. And they are different from what you would have used in 121. It's a totally different machine. And so on and so forth. But yeah, it looks like you don't have a user ID on there, so I will set that up for you. Shoot me an email, and we'll get that squared away today. Um, Working on information about the code behind C's is prime function, since we can't use the function itself. I don't think that is prime is built into C, but there are certainly libraries that have things like that. Um, but we don't need to resort to a library. So we can write our own is prime function. With a little bit of code. So here's a mix of pseudocode and C that will tell you if a number is prime. So f is a possible factor, and I'm going to start f at 2 and go up to and including the square root of n. And if n is divisible by f, meaning that n modulo f is 0, I found a factor, the number is not prime, I can return 0 right there. If I get all the way through this loop and I never returned, that means I never found a factor. That means my number is prime, so I can return a 1. So that's all you need to test if a number is prime, and you can put that in its own function. Call it, my is prime or something like that, and then start building layers outside of that. Recursion hurts my head personally, so unless it's asked of me or super simple, I avoid it like the plague. Probably good to avoid anything that hurts your head, if possible. But recursion is one of those things that at some point, the more you do it, suddenly it will stop hurting your head and it will actually make your head happy. And is that good or bad? Who knows? But that will come at some point. What else are you going to know? You're using prime numbers to add. You're talking about using your own is prime function, right? Thanks. Assignment instructions said implied not to use the is prime. Yeah, so I don't want you to use a built-in prime number checker. You can find libraries that you know you can link in and will tell you if a number is prime, but that takes all the fun out of it. Is the recording for the lecture on right now? Yeah, I'm recording this right now. So if you don't want to be on camera, you can catch me later. All right. Other questions?
So for is prime, it checks all numbers going up by single integers. Is there any like quick way to, because we don't need to include 6 if we've already included 2 or 3. Is there any quick way to get around the numbers that have already been included by their factors?
So we can start making this more efficient. This is pretty efficient. But for example, we really don't need to test even numbers, right? If n is 2, that's going to be prime, but any other even number is not prime. And for this particular assignment, we're going to try to write even numbers as the sum of 2 primes. So other than 4 equals 2 plus 2, we're not really interested in 2. So I could actually start from 3, and I could go up by 2's. And now my loop is twice as fast. I'm only testing odd divisors. But I need to do the special check to see if n is 2 to begin with, if I care about the fact that 2 is a prime number. So that's twice as fast. And you can start doing other things like that. And this will test, you know, for example, the number 9. Well, if something's divisible by 9, it's divisible by 3. So really, I need to check to see if it's divisible by prime numbers. But how many prime numbers are there up to n? Well, you know, it's around 1 over the log of 2. It's certainly for small numbers like, you know, 5 million or something. We're not going to, you know, get this huge reduction of work by testing primes instead of just all the odd numbers. We're probably not going to notice it. And if you're going to check, you know, only prime numbers for divisors, now you have to start storing those somewhere. And since, you know, the bigger your number, the more possible primes, you're going to have some kind of dynamic storage structure like a linked list or something. And so you can do it, but it gets more complicated. Another direction we can speed up is we don't need to take the square root of n. So you know, if your factor is bigger than the square root of n, then my number divided by the factor will be less than my number divided by the square root of n. And n divided by the square root of n is the square root of n. And so you can start playing some games, and what you'll basically find out is that if I compare this to the thing I'm dividing by, when these things flip comparison, I've gotten past the square root. In other words, if f is bigger than the square root of n, then f squared is bigger than n, which means f is bigger than n over f. Now to find this modulus, I have to divide n by f anyway, so if I divide n by f and I compare it to f, as soon as this is smaller, I'm done checking. Right? I know my factor is bigger than the square root. So you can actually avoid calculating a square root, which used to be really expensive, but is, you know, totally unnoticeable time-wise right now. So yeah, you can definitely make a lot of embellishments on here. The main one I would do, though, is only go up to the square root. Don't go all the way up to n, because that's significant, right? 1,000,000, the square root is 1,000, so you have to test about 1,000 numbers. If you go up to n, you have to test 1,000,000, so it's 1,000 times slower if you don't take advantage of the square root cutoff. Let's see. I don't know how it runs on Linux server, but for 500,500 results, basically takes no time. It shouldn't really take a long time. It should barely be noticeable. If you try to run this and it's, you know, printing out one answer every few seconds, you're probably doing a different algorithm. Like you're adding all possible numbers, checking to see if they're prime, checking to see if they add up to n. And that's not the approach you want to take. Do we have to do a call that returns memory after printing an even number? You shouldn't be allocating anything, so there shouldn't be any memory leak issue. And I'm not going to test this for memory leaks. So your local variables get freed when you exit, and you're all set there. Cool. When we were doing proofs, a number of weeks ago, somebody asked what the largest proof was that I'd ever done, and I said I didn't know, but that I could tell them the largest proof I've ever seen. And I get textbook information from the American Math Society every now and then, so I just got this in my inbox. This is 520 pages. This is number 9, part 5, chapters 1 through 8 of the classification of finite simple groups, which I mentioned was probably the most complex proof that I was aware of. And this is one part, 500 some pages. I don't know how many parts there are to it total, but this is all basically one theorem, right, which talks about the classification of these things called finite simple groups. And if these are all 500 pages, this is, you know, at least 4,500 pages worth of proof. And all of this, you know, is broken up into parts and chapters and sections, and this is proving like 2 particular pieces of this larger proof. And it's pretty impressive. It's certainly a singular achievement. So this is mainly concentrating on 2 theorems, C5 and C6. So there you go. I won't put that on the exam though. Let's see, are you compiling your code or just checking to see if we did it? Since you are submitting a PDF. So, I will eyeball your code, and chances are I can tell from, don't take this as a challenge, chances are I can tell from looking at your code if it's plausible that it produced the output that you're submitting with it. But don't try to turn in convoluted code to see if I can decipher it. So I'm not planning to compile your code unless I look at it and something seems really strange, right? In particular, if your program is 3 lines long and doesn't use a division or modulus operator, I'll probably compile it and see. Everything is a challenge if you're brave enough. This is true. But the reason that you're sending in a PDF is in part so that I don't have to compile it and run it, and so I don't have to get very specific about, you know, program requirements and inputs and all that kind of stuff, the way we do in 222, for example. All right, other questions? CSE222 is only offered in winter quarter, and then 223 is only offered in spring, 224 only in fall. But, you know, the lectures are online, so if there's information you're looking for from there, you always have the option of finding that in the videos. And they're all tagged this year, so it should be theoretically more easy to search for subjects. All right, let's go on to applications of the Pigeonhole Principle. So remember what the Pigeonhole Principle says. If you have n plus 1 objects and n containers, and you put objects in containers, at least one container will have at least 2 things in it. Okay, so it's like a doubling up theorem. And it doesn't say that, you know, you might not end up with a container with 5 things in it, or maybe n plus 1 things in it. It just says you can't do that and have each container only have 1 thing in it, or nothing in it. There's going to be something that has at least 2. And there are some non-obvious things that we can prove using the pigeonhole principle. And so I'm going to go through a couple of these as an illustration of how this, you know, fairly obvious sounding observation can lead us to some interesting results. So here's a theorem. Every positive integer has some multiple consisting of only zeros and ones. All right, what the heck does this mean? Well, let's pick a positive integer 1. Well, that's just, you know, it's a number consisting of a single 1, so that satisfies our criteria. If we take the number 2 and we multiply by 5, we get a number consisting of only 1s and 0s. If we take the number 3 and we multiply it by something, what can we multiply this by? Multiply it by 37. That's 111. So that's a number consisting only of 1s and 0s. If I take 4 and I multiply it by 25, I get a number consisting of only 1s and 0s. If I do 5 times 20, I get a number consisting of only 1s and 0s. And the theorem is, if I take any integer, I can find something to multiply it by, which will be, you know, a collection of 1s and 0s. Right? And this is not binary, it's all just decimal numbers. So can we do this for 6? Is there a multiple of 6 that's, you know, turns out just to be 1s and 0s? There is. I don't know off the top of my head what it is. But according to this theorem, there is. Anybody's fingers get cold when they code? Yes, fingerless gloves. They're great, man. I fell in love with them watching Hill Street Blues as a kid. And they're great for coding. And you get style points, too, if you're like in a cafe or something. Uh, 5 times 20 plus 1. So it's got to be just a multiple of your number. No, good way to play with the problem, though. All right, so this is our theorem, and we want to prove this. And it turns out we can prove this using the pigeonhole principle. And it's probably not obvious how that works, because pigeonhole is about counting, and this is about, you know, multiplication and looking at your number written out, you know, in weighted positional notation. So here's how we're going to do this. All right, so here's our proof. And this is illustrative. This is not meant to say, you know, okay, you've seen this, now you should be able to do this on an exam. This is just meant to show you, you know, some of the less obvious ways that we can use something like pigeonhole to prove something that seems unrelated. All right. So so positive integer. Let me call my integer n. So consider the following n plus 1 integers. So I'm going to consider the numbers 1, 11, 111, 1111, and so on, up to and including a 1 containing n plus 1, a number containing n plus 1 ones. Okay, so I've got n plus 1 integers written here, all consisting of only the single digit 1, just repeated different number of times. Okay, now consider congruence modulo n. Write down what each of these is congruent to mod n. And we know that when we write down something modulo n, the division algorithm tells us that we can find a remainder bigger than or equal to 0 and less than n. If our remainder was n, we change that to a remainder of 0. If our remainder was n plus 3, we could change that to a remainder of 3. So if we're getting congruences bigger than or equal to 0 and less than n, there are n possible congruences. All right, so now we make n buckets, and we label them congruent to 0, congruent to 1, congruent to 2, all the way up to congruent to n minus 1. And we place these numbers into these buckets according to what they're congruent to mod n. Right? I haven't given you a motivation why we're doing this, but hopefully you're following along. So we're trying to show that n has a multiple that can be written as just 1s and 0s. Take the n plus 1 integers, 1, 11, 111, and so on, and then place them into these n containers according to what each of these is congruent to modulo n. And now we pull out the pigeonhole principle. We have n plus 1 numbers, and we're placing them into n containers. Pigeonhole principle tells us at least one of these containers will have at least 2 of these objects. All right. So by the pigeonhole principle, at least one container has at least 2 objects. Okay, let me call this container K. I'm going to number these containers. This is container 0, container 1, container 2, container n minus 1, K for container, right? Like compressor. So let's say container K has 2 objects. And let me call these 2 objects n1 and n2. And let's just suppose n1 is the smaller of the 2 numbers, right? Every object is just a string of 1s. Well, now let's do the following. Let's do n2 minus n1. n2 looks like, you know, some bunch of 1s, and n1 looks like a shorter bunch of 1s. And if I subtract, I get a bunch of 1s followed by a bunch of 0s. But here's the kicker. n2 and n1 are both in container K. This means n1 is congruent to K, and n2 is congruent to K. These are both modulo n. So what do I know about their difference? n2 minus n1 is congruent to K minus K, which is 0 modulo n. If this is congruent to 0 modulo n, this means n divides n2 minus n1. In other words, n divides this number, which means this number is a multiple of n. And what is this number? It's a number consisting of a bunch of 1s and a bunch of 0s and nothing else. And that proves your theorem that for any positive integer n, there's some multiple consisting of only zeros and ones. And that's a weird theorem. You know, usually when we prove a theorem, we're trying to prove something, we go step, 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 and we get the answer out at the end. Well, here we have proven that there is, you know, a multiple of n consisting of only ones and zeros without actually finding what that multiple is. We've simply shown that it has to exist. And it has to exist because of this pigeonhole property. So that should feel strange. Well, let me put it this way. If that feels strange, that's kind of expected. So let's play with this for a minute, just because it's a weird result and we worked pretty hard to get it. Let's suppose n equals 6. All right, I'm going to form the following 7 strings: 1, 11, 1, 1, 1. Okay, and I'm going to look at each of these modulo 6. Okay, this is congruent to 1. 11 is congruent to 5. And I'm going to cheat. So, let me grab my cheating calculator. So 111 is congruent to 3. Let me see if I can. So 1111 will be congruent to this will be congruent to 1. And this will actually turn out to be congruent to 5. And this will be 3. And this will be congruent to 1. But I could actually stop right here. Since I know 1, 1, 1, 1 and 1 are both congruent to the same thing, their difference will be congruent to 0. So if I subtract, I get this number 1, 1, 1, 0. And if I divide 1110 by 6, what do I get? 185. Right, if we do n equals 7, I can write down these 8 numbers, and I can look at their congruence, modulo 7. And whatever I come up with, right, since I've got 8 things here, at least 2 of them are going to be congruent to each other. And when I take their difference, I'll have something divisible by 7. Right, so this is like 1 and 4 and 5 and 2 and 0 and 1. So I think these two might give us what we want. Nope, I messed up. Those two. All right, so that's an application of pigeonhole principle, which, you know, again, I think is not very obvious, but, you know, we can prove this, and it's a basic counting argument. But the trick is, you know, figuring out what containers and what objects you want to apply the pigeonhole principle to. And sometimes, you know, a clever application of it will do a lot of hard work for you. All right, so there's a generalized version of this. The pigeonhole principle talks about n containers and n plus 1 objects. A more general version would be given n objects and k containers into which you place those objects, at least one container has at least, and we have some different notation here, funny symbol n over k objects. So this funny symbol is called the ceiling of x, and it's equal to the smallest integer bigger than or equal to x. So it's kind of the opposite side of rounding a number or truncating a number, right? The floor of a number is just throw away the decimal point. So the floor of 2.5 is 2. The floor of 2.9 is 2. The ceiling goes in the other direction. It's the smallest integer bigger than or equal to x. So if x is an integer, the ceiling is just the number itself, because that is an integer bigger than or equal to 2. The ceiling of 2.1 is 3, because that's the smallest integer bigger than or equal to 2.1. It can't be 2 because 2 is smaller, but 3 is the first integer that's bigger than or equal to that. And if we tried the ceiling of 2.99999, that's still a 3. That's the smallest integer bigger than or equal to that. But as soon as we get to 3, right, the ceiling is still 3, but if we go just slightly beyond that, now it jumps up to 4. There's a hole in the ceiling. Better than the bottom of the sea. All right, so this is a function that comes up once in a while, and this is one place it comes up. If you have n objects and k containers, at least one container will have at least the ceiling of n over k objects. Okay, so what does this mean? If n is equal to k, which is equal to 5, so 5 containers, 5 objects, this says at least one container has at least ceiling 5 over 5 objects. Well, 5 over 5 is 1, ceiling of 1 is 1. So at least one container has one object in it. Well, we know that. If n equals 6 and k equals 5, n over k is 1.2, so the ceiling of n over k is 2. And so what does our generalized principle say? If you have 6 objects and 5 containers, at least one container has at least 2 objects in it. That's the pigeonhole principle we've been using. And more generally, if n equals k plus 1, then the ceiling of n over k will be 2. And so this generalized principle reduces to the specific pigeonhole principle we talked about last time. If you have n plus 1 objects and n containers, then you have at least one container with at least 2 objects in it. But we can generalize this in other directions as well. So if you have 25 people, we can put them into 7 containers based on the day of the week on which they were born. And the generalized pigeonhole principle says 25 people in 7 containers. At least one container has at least ceiling 25/7 objects. So 25 over 7 is 3 point something. So ceiling 25 over 7 is going to be 4. So this means if you take 25 people, at least 4 of them were born on the same day of the week. Which you know because at least 4 of them will be in the same container, which, you know, is based on what day of the week they were born. So 25 people, at least 4 were born the same day of the week. Now the pigeonhole principle from last time simply told us if you had 8 people, at least 2 of them were born on the same day. But we can extend that. If there's 25, at least 4 of them were born on the same day. And you can work your way up to this, right? If you had 14 people, it's possible that, you know, they break into 7 groups where 2 were born on Sunday, Monday, Tuesday, Wednesday, right? But once you get to 15, that 15th person had to be born on the same day as 2 other people. So you could do some kind of induction argument, I think, to get to the generalized principle. But this is another version that will be useful in some cases. So if you have 52 cards, and you have 13 of each suit, so you have clubs, diamonds, hearts, spades, 4 suits, 13 of each, total of 52 cards. How many cards do you have to draw to guarantee that you have at least 3 of the same suit? Now you can get lucky. Well, I've been programming way too long, man. Or working at a computer way too long. I wrote this and I looked and I'm like, wait, did I really misspell that? Because it was underlined. I need a break. All right. You could get lucky, and the first 3 cards that you pull off could all be diamonds. And so with drawing only 3 cards, you've got 3 of the same suit, right? But what we want to know is what's the most number of cards that you can draw before you're guaranteed that you have 3 of the same suit. Because I could draw, you know, a club, diamond, heart, spade. Well, there's 4 cards and I only got 1 of each suit. All right, pigeonhole principle generalized comes in here. So make 4 buckets. Clubs, diamonds, hearts, spades. And start putting cards into these buckets as you pull them off. And after you pull off n cards, and you have 4 containers, the generalized pigeonhole principle says we are guaranteed that at least one container has ceiling n over 4 cards in it. So the minimum number of cards to guarantee this, we can rephrase this as find the smallest n such that ceiling n over 4 is equal to 3. Because when that's true, that's the condition that we've got 3 of the same suit. So what's the smallest n that makes this true? Well, you know, play around with some numbers, and we know that, you know, if this thing in here is 3 or greater, then the ceiling will be 3 or greater. So if n is equal to 12, this will certainly, you know, be 3. If n is equal to 11, 11 over 4 will be 2 point something. That will also round up to 3. if n is 8, 8 over 4 will be 2. So the ceiling would be 2. So it looks like the smallest n is going to be 9. Because ceiling 9/4 equals ceiling 2.25, which is equal to 3. Whereas the ceiling of 8/4 is just 2. So you have to get up to 9 cards. So this is all about, thinking about problems in terms of objects and containers. And it's just a different modality of applying some of these concepts. So there's questions in the book about this, and again, same comment I made before, right? You're not restricted to just the problems that I assign for homework. You're welcome and encouraged to look at other problems in the similar problem sets and think about these and ask questions about them, right? And if you want to, come to class or office hours and say, hey, I don't understand how to do question such and such that wasn't assigned, right? We will definitely talk about it. So it's all fair game. All right, so questions? All right, so we're going to move on. We're going to talk about permutations. So we're getting a little deeper into some probability at this point. So definition. A permutation is an ordered arrangement of objects. So permutation is an ordered arrangement of objects. For example, I have a napkin and a phone and a pen. Okay? Here's a permutation of those three objects. The napkin comes first, and then the pen, the phone, and then the pen. This is a different permutation. This is a different permutation. A problem we often ponder is how many different permutations are there of these three objects? And for three objects, it's pretty easy to kind of exhaustively try all the different ways that we can think of to arrange this, and we can probably come pretty close to a correct answer. But it's going to be a question we ask a lot, and it's going to be for things larger than just three elements. So permutation is an ordered arrangement of things. And sometimes we might have n objects, but we may want to talk about what we call an R permutation, which is an ordered arrangement of R objects. So my same three objects, my napkin, my phone, and my pen, but we can ask, how many two permutations are there? In other words, if I pick two of these things and place them in some order, how many different ways can I do that? Well, I could take my napkin and my phone. That's one two permutation. There's my phone and my napkin. That's a different one. Here's my phone and a pen. Here's a pen and a phone. Here's a pen and a napkin. Here's a napkin and a pen. Looks like there's 6 two permutations. Alright, so these are the things we're going to be playing with. Looking at the number of ways in which we can create ordered arrangements of objects. Now the order is important. This permutation is different from that permutation. Okay, there's a notion of first, second, third, and the order is significant. So this might be, for example, you have an Olympic swimming event and you award medals and you want to know who came in first, second, and third. Well, if you have 10 swimmers, how many different ways can medals be assigned? If you give everybody who comes in first, second, or third the same medal, then the order in which they finish doesn't matter. But if the person who comes in first gets gold, second gets silver, third gets bronze, then, you know, having person A, B, C come in a particular order is different from if they come in C, B, A, right? So that's looking at permutations. Okay, so let's do an example. You have 5 students, and we're going to pick 2 of them to stand for a picture. I don't know why. That's kind of a weird thing to do. So we're picking 2 students, and they're going to get their picture taken. And you know, the first student we pick is going to stand right here, and the next student's going to stand right there. So the order in which we pick them is different. We want to know how many different pictures could we take. So let's go back to the product rule. And the product rule says if you can perform a task as a succession of subtasks, then the number of ways to do the task is the product of the number of ways to do each subtask. So our task is pick 2 students to stand for a picture. And we can break that into 2 subtasks. The first task is to pick the first student who's going to stand right here. And then the second task is to pick the student who's going to stand right here. How many ways can we pick 1 student to stand in this first position? Well, there's 5 students. There's 5 ways we can do that. We could pick any of the 5 students. How many ways can we choose someone to stand in the second position? Well, we can't pick the same student twice. They can't be in both places. So we've picked 1 student to do T1. We only have 4 students left, but we can pick any of them to stand in this second position. Product of those is 20, so there are 20 ways that we can pick 2 students out of 5. So the number of 2 permutations of 5 objects is 20. And the idea is whether we're picking students to stand for a picture or medals to assign to swimmers or anything else, right? The calculation does not change based on the specifics of what the objects are. For any 5 objects, the number of 2 permutations will be 20. So this is a useful concept. And like all useful concepts, we want to create some symbols and some language to talk about it. So here's our symbology. So P parentheses N comma R. This means the number of R permutations of N objects. So in this case, we got 5 students. We want to pick 2 of them. We could have simply asked, what is P 5 comma 2? And we would discover the answer is 20. Alright, so let's look at the formula for finding P of NR. So first of all, let's look at P N comma N. Suppose we want an arrangement of n objects taken from a set of n objects. In other words, we're not going to just pick out, you know, the napkin and the phone. We've got 3 objects. We want to know how many ways can we arrange those 3 objects. So this is the number of 3 permutations of 3 objects, p 3 comma 3, or pn comma n. And we can do the same thing we did for the example with student pictures. The task of arranging n objects can be broken into a set of subtasks. Task 1, pick the first object, the object that's going to go in the first position. Task T2, pick the second object, and continue to task Tn, pick the last object or the nth object. Alright, well, we have n objects. How many ways can we pick the first object? Alright, n ways. How many ways can we pick the second object? N minus 1, and so on, until there's only one object left, and the number of ways to pick that is going to be just 1. So the total number of ways to do this task of picking n objects out of n is going to be the product, which we just call n factorial. So Pnn is n factorial. Okay, what if we're only picking n minus 1 objects out of n? All of this analysis still makes perfect sense, except we don't have to pick that last object. So this is going to be n times n minus 1 times n minus 2 dot 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 times 2. We're not going to do that final multiplication by 1. That's not going to affect anything. This is still going to be n factorial. And if that seems weird, think about it like this. If we're only picking n minus 1 objects, we've got to do the exact same amount of work as if we're picking n objects. Because if we pick n minus 1 objects and then we want to pick one more object, it's just going to be whichever object is left. There's no choice in that. So yeah, this will still turn out to be n factorial. I've never done this development like this, and that strikes me as weird. So there's a small chance that I'm making a mistake, but I think this is correct. Okay, but what if we don't care about the last 2 objects? So we're not going to pick the nth object, which we had one way to do. We're not going to pick the n minus first object, which we had 2 ways to do. This is going to be equal to n times n minus 1 we're not going to do that last nth object. We're not going to do the n minus first object. So it's going to be kind of the reverse factorial from n down to and including 3, but not multiplied by 2. And if we go down and we pick only n minus 3 objects out of n, we're going to do this multiplication from n down to 4, but we're not going to pick those last 3 objects. So this is motivational, right? This is trying to get a feeling for some of the ways in which these permutations work. Let me give you the formula. Right? There's the exact formula for the number of R permutations of n objects. And where that's coming from is if we want to multiply, say, the numbers from n down to 4, we can think of it as this. The product of all numbers from n down to 1 divided by the product of numbers from 3 down to 1. Because these will cancel with each other and we'll be left just with, the product down to 4. And so that's what this is capturing. R is the number of things that we're going to pick, and that's how many things we're going to eliminate from the tail of this whole factorial. So P of n comma n is going to be n factorial over n minus n factorial. So 0 factorial is 1. Did you know that? That's just kind of a weird thing. So n factorial over 0 factorial, that's just n factorial. Yeah, one way to arrange 0 things. Right, so P of n minus 1 is n factorial over 1 factorial, which is still n factorial. Yeah, 0 factorial is 1 is one of those things that has to be true, otherwise math breaks. And that's kind of like the nature of math, right? It's because we don't want math to break that we do things a certain way. So it seems like everything just works out nicely, but it's really kind of a ruse. All right, what about P of n comma 1, number of 1 permutations of n objects? Well, according to our formula, this would be n factorial over n minus 1 factorial. And if you work this out with specific numbers, it becomes pretty clear. But that's n factorial. This is n minus 1 factorial. And everything in sight cancels except the n. So this is just n. And that should make sense. If you're trying to pick one object out of n, there's n ways to do it. I can pick the first object, second object, third object, nth object. And so P of n 0 will be n factorial over n minus 0 factorial, which is n factorial over itself, which is just 1. So there's one way to pick no objects from a set of n, and that's just to pick no objects. And this is not a choice function. So the word choose will be something different. When we talk about n choose r, we're talking about something called a combination, where the order does make a difference. And we'll use the symbol C for that. All right, so permutations, right? Ordered arrangement. Choosing combinations, order will not make a difference. We're just picking which ones. So now we can make quicker work of some other examples. So let me put our formula up here. So 52 cards. Pick 5 of them, paying attention to the order. So getting a 2 and a 3 is considered a different hand from getting a 3 followed by a 2. How many ways can we pull out 5 cards from a deck of 52? Well, we're choosing 5 permutations of 52 objects. So that's P52, 5, which will be 52 factorial over 47 factorial. which if you multiply this out, right, on the top it looks like that, on the bottom it looks like this. All of these things cancel, we're just left with that. And that's our good old product rule again. Our task of picking 5 things, 52 ways to pick the first, 51 for the second, third, fourth, 48 for the fifth. And that's the product. That is a big number. So we start using this, every time that we want to do something. We think, well, can I write this as a permutation? So 10 runners and 3 medals. And how many different ways can these medals be assigned? If there's a parallel universe with every possible outcome, how many parallel universes do we need to cover all possible outcomes of first, second, and third place for 10 runners? Well, it's just P 10, 3. And when you're doing questions on this, you should always write down as part of your answer something like that. Because when you start doing the calculations, things can go wrong. Especially if you do this on a calculator. And in general, you would want to write out your answer as something like this. And then multiply it and write down the actual number. But if the person looking at your work sees this, they can say, aha, you understand. You know that this is a permutation. You know that it's a 3 permutation of 10 objects. So this conveys a wealth, right? What if we switch the order? If you switch the order, it's technically a different permutation. So 10 runners, you're picking out 3 of them. This is 10 factorial over 7 factorial, which will be 10 times 9 times 8, which you are right is 720. You got it. So 3 people, 2 places. So you're going to take 2 people's picture out of a group of 3. So 3 factorial over 3 minus 2 factorial. That's just going to turn out to be 6. So let's call these people A, B, C. What are the 6 ways that we can take 2 of them and place them for a picture? AB, AC, BA, BC, CA, CB. There you go, 6 different permutations. Yeah, it doesn't really make sense to do P3, 10. So number of ways you can pick 10 things out of 3. And that will make your factorials go negative, which is also a thing. You can look up the gamma function if you want to know why 0 factorial is 1 and why the factorial of 1/2 is related to pi and all kinds of good things like that. Yeah, pi is everywhere, man. Alright, if you have 3 people and you want to select 3 of them, that's going to be 3 factorial over 0 factorial. Well, that's also 6. So what are the 6 ways that we could pick 3 people out of 3? And how did I get those? I took my answer from here and I just added whatever the unused letter was. Right? That's the sense in which picking the last element, you have no freedom of choice in that. If I've already picked an A and a B, I have to pick a C. If I've already picked a C and an A, I've got to pick a B. So the number of 3 permutations will be the same as the number of 2 permutations. So this stuff starts to make sense at some point. which is good or scary or both. So suppose we want arrangements of the letters A through G that contain the word cab inside. So if we just look at, 7 letters A through G, the total number of permutations of those would be, pick 7 letters out of 7, and that's just going to be 7 factorial. What if we want to know how many of those contain the string CAB? Any idea? Set up some containers. P103. So this is an annoying question because the answer is so trivial once you've seen it, but it's really, really subtle if you haven't seen it. So I'm going to rephrase this problem as the number of 5 permutations of these 5 objects, CAB, D, E, F, G. And any arrangement of these 5 objects will be an arrangement of these 7 objects containing CAB. And any object containing CAB will be an arrangement of these 5 objects. And so the number of ways you can do this is just 5 factorial. So this is an example of where sometimes we want to change the problem, right? This is a key for computer science, right? If you don't know how to do a problem, do a different problem that you do know how to do. And then, either change the original problem into that or somehow convince someone that it's the same thing by making it the same thing. Yeah, that one intrigues me. All right, so those are permutations. The other thing we want to talk about is unordered arrangements, and that's what a combination is. So a combination is an unordered arrangement of objects. And I remember this because it's backwards from common sense. Combination locks should actually be called permutation locks because the order of the numbers matters. So a combination is an unordered arrangement of objects. And again, an R combination is an unordered arrangement of R objects. Locks would be easier to break if the order didn't matter. But how much easier? How many combinations are there versus the number of permutations? So let's go back here. 3 people, 2 places. The number of 2 permutations of 3 objects was 6. But if we don't care about the order, how many combinations do we have? We have AB, we have AC. BA is the same as AB, so I'm not going to count that. We have BC, that's a new one. CA is the same as AC, and CB is the same as BC. So the number of two combinations of three objects looks like it's only 3. So we can talk about Cn comma R. And that's the number of R combinations of n objects. And this is sometimes called n choose R. And we have another notation that you'll see and we'll use a lot, which is this. Two numbers in parentheses, one on top of another. This is not division. Don't put a line here. This is like a little 2x1 matrix symbol, but it's not a matrix. It's just a different notation. When you have two numbers inside parentheses, we can use that to represent n choose R, R combinations of n objects. Yeah, so you'll see that in LaTeX, for example. All right, so P3 comma 2 is equal to 6. We would say C3 comma 2 is equal to 3. Or we could write 3 choose 2 is equal to 3. Now here, if we wanted the number of 3 combinations of 3 objects where the order makes a difference, well, every one of these, the elements are in a different order. But the 3 elements I chose here were ABC, the 3 elements here were ABC, 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 ABC. There was only one way to choose 3 things out of 3, and that was to pick each thing. If I want to pick one object out of 3 where the order matters, I got 3 ways to do that. I can pick A, I can pick B, I can pick C. If I wanted to find the number of unordered combinations of one object taken out of 3, that's also going to be 3. I can pick an A, I can pick a B, or I can pick a C. So sometimes the number of combinations is smaller than permutations. Sometimes it's a lot smaller. Sometimes it's the same. It's never going to be bigger. And so we can find a formula for this. And it's actually the number of ordered arrangements divided by the number of possible orders of R objects. So the number of ordered arrangements of R objects taken from n divided by the number of ways we can rearrange those R objects. Well, if you have R objects, how many ways can I arrange those? Well, that's just P R comma R, which is just R factorial. Or I can go back to my product rule. I choose which object comes first, which one comes next, which one comes third, and so on. I can find, the first object R ways, the next one R minus 1, and so on. This will be R factorial. And so if I put that together, P of nr was n factorial over n minus r factorial. And then if I divide that by r factorial, I just put another r factorial on the bottom. So let me collect these. So these are ordered arrangements, n factorial over n minus r factorial. Number of combinations, which we write like this, is n factorial over n minus r factorial times r factorial, and that's unordered. And those are the two main formulas we're going to deal with for this part of our discussion. Factorials do not subtract like that. So n minus r factorial in general is not equal to that. Except for fringy cases. So 5 minus 2 factorial is 6. 5 factorial is 120. 2 factorial is 2. Where are we? We got 2 minutes and 20 seconds left. We can start a few examples, but we'll get into the bulk of this on Friday. But a few examples. Number of poker hands. So you're playing poker, you have 52 cards. Every card is unique, but the order in which you get your 5 cards makes no difference. So you're choosing 5 cards out of 52, the order does not matter. So this is 52, choose 5, which will be 52 factorial over 47 factorial times 5 factorial. And if you write these out, right, this is going to end up being an integer. That's not obvious. But, you know, obviously the 47 factorial will cancel the first 47 terms of this factorial. But that 5 factorial will cancel some of the remaining pieces of the remaining terms. And you'll end up with an integer. And what you end up with is the number of ways that you could, you know, order 5 cards out of 52 divided by 120. Because for any set of 5 cards, there's 120 ways you can rearrange them. And if we don't care about those, then we factor out 120 from the number of permutations. If we want to pick 5 people out of a group of 10, without regard for what order we pick them in, that's 10 choose 5. So 10 factorial over 5 factorial times 5 factorial. Now this is just a pair of formulae, and we can use these when we're given a problem like, you know, how many ways can you choose r things out of a set of 10? We can just pop r and n into here and come up with our answer. But if we play with these in different situations, we can start to glean some understanding of what's going on here. And we're going to start off with that on Friday. We're going to look at some bit string questions, and this is going to lead us into something called Pascal's triangle and the binomial theorem, which are related. So this will get a little headier, but it's fun stuff. And it's just different ways of looking at you know, where we can take these basic counting arguments and draw some inspiration from them. All right, so we will do that on Friday. Have a good afternoon. I will see you next time. Thank you.